Hi everyone, let's start our lesson today. Today we're going to talk about 2.2, which is the limit of a function. First, take a look at this function here. This is a quadratic function. Now, if you factor this, it's going to factor into x minus 2 times x plus 2. So the x-intercepts are 2 and negative 2. So this is a graph for this quadratic function. It is a parabola at the 2 x-intercept here and here. Now, take a look at this function over here. As x approaching to 1 from the left side and from the right side. So when x is getting closer and closer to 1 from both sides, what do you think about the function value f of x? Well, the function value f of x, as the x getting closer and closer to 1, then the y value, the function value, is getting closer and closer to this number, which is negative 3. So we say that the limit of the function as x approaching to 1 is equal to negative 3. Another way to express this is use this notation. So LIM here stands for limit. So the limit of f of x as x approaching to 1 from both sides is equal to negative 3. Now notice that when you say approaching to 1 over here, you actually indicate that it's approaching 1 from both sides. So this is actually from both sides. The y value will approaching to negative 3. So as x approaching 1 from both sides, y, which is f of x, is approaching to negative 3 here. Okay. So another way to say this is we say f of x is approaching to negative 3 as x approaching to 1. Now we can say the limit of f of x as x approaching to 1 is equal to negative 3 if we can make f of x arbitrarily close to negative 3 by taking x to be sufficiently close to 1, but not equal to 1. So if we want f of x to be close to negative 3 within a certain range, and take x over here to be close enough to 1. So the corresponding f of x value will be close to this negative 3 within the range that you want, okay? All right, so now over here we have 3 examples over here, 3 cases, okay? Now the difference between them, okay, this is actually, this one, the curve here has no break, okay? There's no break at A, okay? This one here, there is a break over here, a gap over here at A, okay? Let me indicate that. You have a gap over here, okay? And then the function value over here is actually defined to be a different number, which is not equal to this L over here. So the function value will be over here, okay? Now what about the last one? Now the function is not defined when x equal to A, so you have a gap here also. So the difference between this one and this one here is the function is defined when x equal to A. The function value is defined to be this corresponding number over here. This one over here, the function is actually not defined at A. There's no function value at A. This is an open gap over here, okay? Now, out of these 3 cases, let's think about what happened when x approaching A from both sides. When x approaching A from both sides, okay, let's move along the curve, remember? So what happened to the function value over here? Well, the function value is getting closer and closer to this L over here. Again, for the second case here, when x approaching A from both sides, along the curve, on the left side, the function value approaching to L. On the right side, the function value approaching to L also. So the limit of f of x will be equal to L, okay, in both this one and this case and also this case. What about the last one? Well, when x approaching the a from both sides, let's say from the left side along the curve, f of x is approaching to L here. What about on the right side? Move along the curve. When x is closer to a, again, the function value is approaching to L also. In all three cases, the limit as x approaching to a is equal to this L over here. Okay, so all three of them have the limit of f of x as x approaching to a is equal to L. Now take a look at this example here. So I give one more example. Over here, we have this function. There's a gap here. The function value when x equal to 1 is actually equal to 3. So f of 1 will be equal to this 3 right here. Now, what happened for the limit as x approaching to 1 from both sides? The limit of this f of x, let's move along this, the graph of this function. If you move along this graph, and when x approaching 1 from the left side, let's see what happened. Well, f of x is approaching to 2. What about on the right side when x approaching to 1? Remember, you have to move along the graph right here. So move along the graph when x approaching 1 from the right side. Again, f of x is getting closer and closer to the 2. So the limit of this function as x approaching to 1 from both sides, that's equal to 2, not 3. Okay, so it's equal to 2, not this 3 over here. Okay, so you have to move along the curve. Okay, now the next one, let's guess the value for each one of this limit here. Now take a look at this limit. Now think about this. This is a function of x. Let's call it g of x. When you factor the denominator, we'll factor that into x minus 1 times x plus 1. And the x minus 1 is going to divide out. Okay. Now, before you actually divide out this common factor up and down, let's think about the domain for this function. Now, this is in the denominator. In order for this rational function to be defined, we need the denominator that's not equal to 0. When does this denominator equal to 0? This denominator is equal to 0 when x equal to 1 and negative 1. So in order for this function to be defined, the denominator cannot be equal to 0. So the domain for this function is all real number x such that x does not equal to positive or negative 1. So that's the domain for this function right here. Remember, for rational function, the denominator cannot be equal to 0. So we have to exclude those numbers that make the denominator equal to 0. Now, after that, you will divide out this common factor x minus 1. Now, after you reduce them, remember that we still have the same domain. X does not equal positive or negative 1. So this function, this original function g of x is equal to this, but with this domain. So in this case, over here, we still have x does not equal to positive or negative 1. Even though if you substitute 1 here, it looks like we get a 1/2, but 1 is actually not in the domain for this function. So you have to exclude the 1. Okay, now how does the graph of this function look like? Now we know the graph for 1 over x plus 1. So it's going to be here and also over here. Okay, it should have 2 parts. But let's focus the part over here, okay? Because when we're just interested in finding what happened when the limit as x approaching 1. So I'm going to look at this part of the graph right here, close to 1, okay? Close to when x equal to 1, okay? Now, we know that this function is equal to 1 over x plus 1 with x does not equal to 1, which means 1 should not be in the domain. 1 is not in the domain for this original function. So we had to make this a gap right here. Instead of a solid dot, it should be a gap. So we have to take away this single point. It is so tiny, you probably won't be able to see that on your graphing calculator. But I just make it a little bit bigger to exaggerate that a little bit so that you can see that better. So it is actually a gap right here, okay? So now if you take a look at the graph right here, what happened when x approaching 1 from the left side? Well, along the curve, you see the function value is closer to 0.5. Now, how did this 0.5 come from? Suppose you don't have a graphing calculator. You can plug in x equal to 1 into this function. When you have 1 over here, x equal 1, so you have 1 over 1 plus 1, so that is equal to 1/2, which is 0.5. So if there's no gap over here, then this point will have the y coordinate to be 1/2, which is 0.5. Now, because we have to take away this point when x equal to 1, so we make this a gap. However, as you can see that if you move along the curve when x approaching 1 from the left side and also from the right side, the function value is getting closer and closer to this 1/2. Okay, so what will be this limit as x approaching to 1 from both sides? The function value, this function, is getting closer and closer to 0.5. So this limit over here is equal to 0.5, or you can write down 1/2. Number 2, we're trying to guess the limit for sine x over x as x approaching to 0. Okay, well, we need the denominator that's not equal to 0. So we'll have the domain for that will be x, all real number x, such that x does not equal to 0. Denominator cannot be equal to 0. Now, if you graph this function, you see this is the part of the curve when x is close to 0. You see that this should be a gap right here because when x equals 0, this is undefined. So you should have a gap right here. Okay, so this is an open gap. Okay, so now you can also make a table and see what happened. Okay, when x getting closer and closer to 0 from both sides. So you see those numbers here, plus or minus 1/2, plus or minus 0.1, plus or minus 0.001. So those are numbers that are getting closer and closer to 0 from both sides. So you see that when you choose those x value that are closer and closer to 1 from both sides, what happened to the function value? Well, there's a pattern here. You see that they're getting closer and closer to 1, right? As you observe from the graph right here, when x is getting closer and closer to 0 from the left side and the right side, the function value, the y value here, is getting closer and closer to 1 right here. Even though the function is not defined when x equals 0, there's a gap here, but the y value is getting closer and closer to 1, okay? So now we can conclude that the limit of this function as x approaching to 0 from both sides, that's equal to 1. For now, this is only a guess, right? In fact, this is correct. We can prove this using a geometric argument in chapter 3. Number 3, we're trying to find the limit of this function as x approaching 0 from both sides. Now, if we graph this function, you see the graph is going to be like this.
On both sides?
Well, sometimes it is 1, the function value, and then -1, and then go to 1, -1, 1, -1, and oscillate infinitely often between 1 and -1, and also take out the value that are in between 1 and -1. So it oscillates like crazy right here. The closer you get to 0, the frequency that you oscillate will be increasing. As x approaching 0 from the left side and the right side, the function does not approaching to a fixed real number, and we say that the limit of this function does not exist. DNE stands for does not exist.